Okay, so I'm going to continue on with, in this case, we're going to look at binary search. So we're continuing on with searching of ordered lists. So the lists have to be in order, okay? We already looked at sequential search and modified sequential search. And now I'm going to look at binary search, okay? So binary search is basically what you're doing is you iteratively split the list in half. So you keep shrinking the size of the list. You're basically cutting it in half time after time until either you find the item or you get to a point where you can determine that the item is not in the list. Okay. And the basic way that's done is that you have three variables. You have one called the middle element. So this is a pointer that points to the middle element in the list. Okay. The next thing you do is you have another pointer that, or this is like an index, an array index essentially. These are all array indices that points to the bottom of the list, and the other one that points to the top of the list. So typically, in when we're doing ascending order, the top of the list is the smallest item, and then at the bottom of the list is the largest item. Okay, so you have you keep going through this process. You keep searching and splitting the list in half, splitting it in half, splitting it in half, until eventually you find it, or you don't find it, right? So you find it and then you can just return its location, or you don't find it, and what happens is these two cross over, right? Bottom and top. One becomes larger or smaller than the other, depending upon if it's ascending or descending. And when you have that crossover, then essentially you terminate your search function and you send back something to indicate that the item's not in the list. In our case, in the code that we're going to look at, it's actually a -1. Okay. So let's take a look at an example. Let's assume that here's your list. You have these 10 items in your list, and you are looking for this number 43. Okay. So you're looking to see if number 43 essentially is in your list. Okay. So this is what you start off with, 10 items. Okay. And you have this index top, which actually points to the top of the list, the smallest item. And you have another one which points to the bottom. So then what you do is you use those two to figure out your midpoint in your list. Okay. So first time what happens is you point to this item, and this item. So first iteration through the loop of your binary search. Okay. Then what happens is that you do a comparison. Is 28 equal to 43? No. Is 43 smaller than 28, or is 43 larger than 28? If it's larger than 28, what happens is this value, top, gets modified. Top will then just indicate, it will just be mid plus 1. Okay, so you take whatever it was before, you set it to mid. In this case, it was 0, 1, 2, 3, 4. So it was 4. So plus 1 gives you 5. So now it points to the fifth item in the list, right? So we basically just chopped away this part of the list because we know it's not there, right? Because it's ordered. It has to be ordered. Okay. The next time this runs, what happens is you look at, you get here, you have a new top, you have a top, and you have the same old bottom as before. And you go to the middle of the list and you look again. Is 43 smaller or larger than 56? Well, in this case, it's smaller. So what happens now is that and you see the midpoint was 7, of course, from the original part of the list. Now what we see is our new list is just going to be these two. Okay. And now the new midpoint, of course, because now we've changed the bottom. So the bottom pointer now points to mid -1. So now it's, instead of pointing at item 7, it's pointing at item 6. Okay. So then now you have these two left. And depending upon the algorithm, how it works is it might point to this one or this one because it's an even number of items. In this case, for this algorithm, it's pointing to this one. And then what happens here is that it points to this one, checks it. It's now item 6, and it finds it, okay, and returns it, okay? So they're both equal, which is fine. You just want the crossover in this case, okay? So 43 is found, and you would return that location. Okay. Now what we'll do is we'll take a look at the code. What I had already gone through and created a binary search function. And what I'll do is I'm just going to open it, and I'll put this code up on the website underneath the source code area. So I'll just go through and explain the different parts of this, and I went through and put comments in already. But basic idea here, this is a simple example implementing the binary search function. Okay. So first thing is I'm going to do is I'm just going to, actually the first part here is the actual function definition. Okay. And I got this directly from the textbook, pages 378 and 379. Okay. And the only thing I changed was I call this made this double and double here. Okay, so this is the list. So the items I put in here, notice that these are the array items are actually floating point numbers or numbers with decimal values. So I just changed that to double. And then the value I'm looking for, I also changed that to a double data type. All right. And the other part of this, of course, is you need to include the function prototype. So the function prototype, here is the array. It's a double data type because that's for my implementation, I changed it to double. Here is the size. So it's the data type of the size of the array. There's 5 elements in this array, so I'm actually going to pass in a 5 for this. And the last one is the actual what I'm looking for. Okay, this is the data type of what I'm looking for. Okay, so here's the prototype, and it matches, for the three parameters that are defined here. Okay, so in the function definition, what we have is we start off with, here is our top of our list, okay? So we set top equal to 0. This is one way we can actually initialize a variable. In this case, it's an object, but it essentially works as the same thing as a variable. We're just saying top is equal to 0. Bottom is equal to 5. In our case, I'm passing in a 5 here, okay? So 5 minus 1, so this would be 4. For this example, it'd be 4, okay? And always top is always going to be 0 for any of our items, so we keep that as 0. This one is actually being passed in here. And then mid, this contains the middle point of our list, okay? So this is our crossover. So if it happens that top is no longer less than or equal to bottom, and it becomes equal to bottom, typically what will happen then is that this will end, and then you'll return a -1, which means essentially that you didn't find it in the list, okay? All right, so the next thing we have here is we calculate the value of the midpoint. So we take whatever the top is, whatever the bottom is, and we divide it by 2, okay? And when we do that, this will give us our midpoint. So if you look at like our example here, we had 5 items in our list, and we're looking for, in this case, 6.2. And what will happen here is that top was 0, bottom was 4. So we're going to have 4 top plus bottom. So we're going to have 4 divided by 2. So our first location of the midpoint is actually location 2. Okay, so 0, 1, 2. So it's going to be looking at this value and trying to make a comparison the first time through this loop. Okay, so what do we find? Is it equal to it? No, it is not. Okay, so it's not equal to it. So then we go down to here. So we do an else. Is this value greater than value? The middle value, what we looked at, is it greater than what we were searching for? Okay, the item in the list that we're actually making a comparison with, is that greater than what we were looking for, which was 6.2? And the answer to that is yes, it is. Okay, so what that means is our item's got to be somewhere in this part of the list, or not be there at all. Okay, so then it is true. So now the bottom of the list gets modified. So the bottom of the list is now pointing to this here. So here's the top and here's the bottom. So now we go back up to the top here. So the top was item index 0. The bottom is index 1 the next time we run through this. Okay, so top is 0, bottom is 1. Good. We're still good. So we still run this. So what we next do is 0 n1 over 2. So our midpoint now becomes 0. All right, index 0. So we check it. Is it equal to value? No, it's not. Okay. And the reason it's 0 is, of course, because it's 1 over 2, and this is integer division, and it will give us either a 0. It will give us a 0 because it just truncates this number. So then we say if list mid is greater than or equal to value. In this case, it is not. It's false. So now bottom becomes mid minus 1. So it becomes bottom becomes equal to mid minus 1. So now mid was 0, and this is minus 1, so this becomes a minus 1. Then we go back up here, and then what you find now is you see that bottom was minus 1, top is 0. So this is no longer true. So it just breaks out of here and returns a minus 1. Okay? So if we run it, so now this all has, I put all the code in here. Oh, yes. So other part of this, here's me actually executing it, right? So I pass in array. This is the call. This is the function call. So I pass in the array, the size, and the value I'm looking for, which is 6.2. Okay? So it's going to give me the location. So, of course, in this case, 6.2 is not here. So then, because it's not here, it will pass back. It will send back a minus 1. Okay? So we run it. And there it is, not found. And the reason it's, so if it finds the location, it's minus 1, it just displays this message, okay? So it says not found. So now if we run it, of course, with something else, let's do 10.5. We run it. Found that location 3. 0, 1, 2, 3. So it's at location 3, okay? Now, when this one runs, when it runs this time, what would happen is that, of course, these two are the same. This is still 0. This is 4. So it goes through. It says top is less than or equal to bottom. Good. And then it looks at it. It says mid is the middle, which was 6.7. So it's still, not 6.7. Mid will be pointing to 6.7. So it's going to check. Is 6.7 equal to 10.5? No, it's not. So this is false. So it goes to here and checks here and says, okay, is the list value greater than the value we're looking for? No, that's not true either. So what will happen is that it will go to this. And top will now equal to the mid plus 1, right? So initially mid was 2. So top will now equal 3. Goes back up here. It says top top is equal to 3. Bottom was still the same location, right? Still 4. So this is still true. Then it splits it in half again. Well, it just says top, which was 3, plus 4, 7. So this will give you a 3. So it's actually giving you a 3. To come back, right? Because it's 7 divided by 2, which is going to give us 3.5, and it just truncates it. Now it looks at it. It says list location 3. Is that equal to the value? Yes, it is. So now this one will return the middle value and come back out here. And location would now be 3. Okay? So that's the basic operation of binary search. Here's the entire code for this thing. I don't know why it's giving me this. It's not giving me an error, but it shows that code for some reason. Okay. So I'll leave this code. I'll put this code on the website for you to look at. But let's see. Okay, so just run it. I really don't know why. It's like leftover from something else. File. Save all. Oh, okay, so we're good. All right. Okay, so I'll put this on the website, but that's essentially it. That's how a binary search function works. It's an efficient way of searching. It's a lot more efficient than sequential search. And any like any kind of searching that you do with any kind of list of a significant size, binary search is the way to go. For really small lists, sequential search works fine. But that's the basic idea behind it.